Welcome. So I'm Dr. N. Baladastagiri. So in the series of video lectures that we are going to discuss on the digital circuits concept. So the first lecture is regarding the data converters. What is a data converter? So a data converter is a circuit which converts the analog signal into the digital representation, and and also it can convert the digital signal into the analog signals. So these can there are digital converters which can convert analog signal to digital representation, and from the digital representation to analog representation. So now, why these data converters are important? Okay, so why they are playing a crucial role? Why? Because uh, as today's world is digitalized, so whatever the products we are using, so these products will perform the calculations mostly in the digital or discrete time domain, but the naturally occurring signals are the analog signals. So therefore, in order to process uh, these gadgets or these products, we need to convert these analog signals into the digital signals. And in order to get back the original analog signals, so again we have to convert the digital representation into the analog signal. So therefore, it is very, very important for us to know about the data converters concepts. Okay. And before going into the fundamentals of these data converters and also the specifications of these data converters, so first let us look at the difference between the analog as well as discrete time signals. So let us see the differences between analog and discrete time signals. Okay, yeah. So before that, as we have seen these data converters, there are majorly two types of data converters. One is the converter that converts analog to digital, which is known as the analog to digital converter. So this is referred to as A by D converter or ADC. Similarly, the data converter, which is used for the conversion of digital data into the analog representation, it is referred as digital to analog converter. So which is taken as D by a converter or DAC. Okay. So in order to illustrate these two operations, let consider a small circuit here. Circuit nothing but is a small operation here. Okay. So first consider a continuous time signal here. Okay, so it is a continuous time signal. So in order to convert these continuous time signal or analog signal into the digital domain, so first we have to use the low pass filter. So whatever the analog signal is taken, that has to be given to a low pass filter. So because so this analog signal is filtered, so is filtered in order to overcome the anti-aliasing effect. That is aliasing effect. So this low pass filter, what you are using here is a anti-aliasing filter. Okay. So after passing through a low pass filter, so the same signal is given to the sample and hold circuit here. Okay. So the sample and hold circuit plays a crucial role in determining the accuracy of analog to digital converters. So in the later sessions on in the later videos, we can see about more in detail about the sample and hold circuit here. So the signal which is given to the sample and hold circuit is sampled and held and then converted into the digital signal. Okay, so by using the ADC. So once it is converted into the digital domain, the signal looks like this. Okay, so we get the discrete uh, samples here. So it is the signal what you are getting. So it is defined at only at discrete time intervals. Okay. So now again, if you want to convert these digital signal into the analog signal, so we have to use the DAC here. So that is the digital to analog converter we have to use. So once we have given this digital signal to the DAC, the output of this DAC looks like this. Okay. So the output of DAC will look like a staircase signal here. So it looks like a staircase signal. So it looks like a staircase signal, which we have seen here. So let it be C here. So this analog signal, let it be A, and the signal is let the discrete signal be B here. Okay. So now, in order to get back the original signal here, so we have to send this staircase signal through a low pass filter here. So send this signal to a low pass filter. So this low pass filter will eliminate the higher order signal components, so which are caused by the conversion. So after sending it to the low pass filter, the output of low pass filter will look like this. Okay. So here the smoothing of the signal will be taken place by removing the higher order components, which is caused due to the conversion. Okay. So this is how you can convert a signal, that is the analog signal, into the digital, and from the digital back into the analog here. Okay. So this example here illustrates the main differences between the analog and digital signals. Okay. So if you see the figure A here, okay, so which is analog signal, this analog signal is continuous in time and it has infinite value. The figure B, so which is a digital signal, so it is discrete with respect to time and it is quantized. The term continuous time signal reflects to a signal whose response with respect to time is uninterrupted. Simply, we can say that the signal has a continuous value for the entire time period for which the signal is present. By referring to the analog signal as infinite valued, we mean that the signal can possess any value between the given voltage levels. For example, if the peak voltage, that is the peak amplitude of the sine wave is 2 volts. Okay. So therefore, this signal can have any value in between plus 2 volts and minus 2 volts. So we cannot measure each and every voltage of this. So for example, at this point, so the signal voltage may be some approximately 1.9119213 like this. Okay, so this exact precision of the signal we cannot measure. Okay, so there is no equipment, laboratory equipment, that we can measure the continuous value with the accurate precision. Okay, or with the infinite precision. So therefore we can say that analog signal is a continuous time signal, so with respect to time. Okay. So the digital signal, on the other hand, is discrete with respect to time. So this means the signal is defined only for certain or the discrete periods of time. Okay. A signal that is quantized can only have certain values, uh, for discrete time period. So this is about the differences between the analog versus discrete time signal. So now let see into the concept of converting the analog signal into the digital signal. Okay, so converting analog signals into digital signals. Yeah. So we have already seen the differences between the analog and the digital signals. So now we see how it is possible to convert from analog signal to digital signal. So for explaining this process, let us take an example here. So let us take an example of temperature here. Okay. So we temperature here. Suppose we had a thermometer. Okay. So this thermometer has only two readings, that is hot and cold. Okay. So we are taking a thermometer, so with two readings, that is hot and cold. And if you want to record the weather patterns and plot the results, so as this thermometer is having only two readings, so here we can able to take only two quantization levels that can be correlated with the actual temperature. Okay. So for example, if the temperature is in between 0 degree Fahrenheit to, so or else 0 degree centigrade to 25 degrees centigrade here. So this temperature is recorded as cold. Okay. So if the temperature is in between 25 degrees centigrade, okay, to 40 degrees centigrade. So this temperature is regarded as hot. Okay. So as the thermometer, what you are taking here, this can has only two readings, that is hot and cold. So therefore, I am taking only two quantization levels. Okay. So these two quantization levels can be correlated with the actual temperature as far as seen here. So that is if temperature is in between 0 to 0 to 25 degrees. So this reading is taken as cold, and if the temperature is in between 20, sorry, you can take it as 26 here. So if it is in between 26 to 40 here, you can take it as hot here. Okay. Now what you are doing is that, so we are measuring the temperature every day in the afternoon. Okay. So and after 1 week, so if you are going to plot the results, okay, so if you are going to plot the results, so let us see how you get the graph here. So let us see how you get the graph here. So it is time here. So it is time. So Monday. So it is Monday. Uh, so take it as Monday here. So it is Tuesday. So Monday, Tuesday, Wednesday, Thursday, Friday, and so take only 5 week a day. Okay. So Thursday, and also the temperatures is so it is 0 degrees, so 10 degrees, 20 degrees, 30 degrees, and 40 degrees. Okay. So here what I have taken is, so on the x-axis I have taken the days, and on the y-axis I have taken the temperature in terms of degree centigrade here. Okay. So now I'm going to plot the temperatures that were recorded. So randomly I am plotting here. So randomly I am plotting. Yeah. So I have plotted this here. Okay. So now from this figure here, so what you can see here, so it is not a even though we have taken the two quantization levels, this does not replicate the digital signal. So it looks like a continuous signal here. Okay. So now what you do is that, okay, uh, now plot this here. Now what you do is that, so now as per the quantization levels, take it here. Okay. So now for example here, so from 0 to 25, so this quantization level is cold here, and above that it is referred to as hot here. Okay. So and above that it is referred to as hot here. So it is the binary representation of the analog signal, so that we are taking one sample per day. So we are taking on Monday one sample, we are taking Tuesday one sample, we have taken Wednesday one sample, we have taken. So for example, Monday this is the temperature. So Tuesday this is the temperature. Okay. Okay. Wednesday this is the temperature. So Thursday this is the temperature, and Friday this is the temperature. Okay. Uh, so so from this figure, it is apparent that, so your digitalized version of the weather is not an accurate representation of the actual weather. So now suppose you take one other thermometer, so which can able to which record the four possible temperatures. Okay, four possible temperatures it can able to record. So that is, if the temperature is in between 0 degrees centigrade to some uh, 12 degrees centigrade, so it is recorded as cold. So if the temperature is in between 13 degrees centigrade, so it is represented as cold here. So if the temperature is in between 13 degrees centigrade to 25 degrees centigrade, so it is represented as cool. Okay. If the temperature is from 35 degrees centigrade to uh, some 32 degrees centigrade, so it is referred to as warm. So if the temperature is in between 32 degrees centigrade to 40 degrees centigrade, so it is referred to as hot. So now as per this, you just see here. So now here, so from 0 to 12 degrees centigrade, it is referred to as cold. From 0 to approximately 25 degrees centigrade, it is referred to as cool. Okay. So from 25 to 32 degrees centigrade, so it is referred to as warm. So above 32 degrees centigrade, it is referred to as hot here. Okay. So now if you plot the graph for this, so on Monday, so you get the temperature on any one of these quantization levels. Okay, so here also if you take the digital version of the weather, still looks like nothing the actual weather pattern, that is like a continuous signal, but critical issues in digitalizing analog signal should be apparent. The actual weather pattern is the analog signal, so it is continuous with respect to time, and its value can be anything in between the 0 degrees and 40 degrees. The accuracy of the digital signal depends upon the two things. So one is the number of samples what we have taken. So number of samples what we have taken, and also on the resolution. Okay, so and also on the resolution. So these two are the two key things that we can able to represent the accuracy, represent the digital signal with an accuracy here. Okay, so now for example, now consider a thermometer here. So a thermometer here. So this thermometer has 25 temperature readings. So consider a thermometer, so which has 25 temperature readings, and this can take the readings 8 times per day. So 8 times per day. So 8 times per day. Okay. So therefore, what you can see is, so what you can see is, so so it is up to this, it is Monday, so Tuesday, Wednesday, Thursday, and Friday. So it is Monday, Tuesday, Wednesday, Thursday, and Friday. So we are taking the temperature 8 times per day. So that is 1, 2, 3, 4, 5, 6, 7. So take it here. So 1, 2, 3, 4, 5, 6. So let us take here also 7 and 8. Okay, 8. Okay. So now the total temperature readings we are taking is 25. So for example, so every 2, 4, 6, for every 2 degrees centigrade, you plot the y-axis for suppose. So 18, 20, so 22, 24, 26, 28, 29, 30, 32, 34. So I'm just drafting it roughly. Okay. So 40, 42 up to 50 degrees centigrade. So Monday for the first time when I have taken early, so in the given 8 times, so when Monday in the early morning, the first time I have taken, the temperature is 8. Okay. Next, second time the temperature is some around 14. So third time when I took, the temperature is some 20. Okay. So fourth time when I have took, the temperature is approximately 24. So fifth time when I have taken, the temperature is approximately 30. So again, for the sixth time when I have taken, the temperature has dropped to 24. So later it is some 18. Okay. So like this, so every day, 8 times per day. So with total 25 readings, the temperature is recorded. Okay, the temperature is recorded here. So therefore, if you see this graph and compare with the previous graphs here, so uh, what you can see is that the digital version of the weather is approaching that of the actual analog signal. Okay, so if we keep increasing the sampling time and resolution, so here the resolution is it is nothing but the number of quantization levels. That is, if we increase the sampling time and the number of quantization levels, the difference between the analog signal and the digital signal would be negligible. Okay, so this thing we have to keep in mind. Okay, so what we have to keep in mind so far is that, so in order to make the analog signal and digital signal to as the same, that is, in order to reduce the difference between the analog signal and the digital signal, so what we have to make sure is that, so for the digital signal, sampling time and resolution or quantization, number of quantization levels should be high. Okay, so should be high here. So this we have to keep in mind. Okay, so now this again brings up new critical issue. Okay, so what is the issue? So in order to reduce the difference between the analog signal and digital signal and make them the same, so we are increasing the sampling time, as well as, so we are increasing the resolution or the number of quantization levels. Okay, but the thing is that, how many samples how many samples we should take in order to accurately represent the analog signal. So the question is here again, how many samples should we take in order to represent the analog signal? Okay, with the same example what we have seen here. So let us see. Suppose this is today is Thursday. So Thursday we are reading the temperature 8 times per day. Okay, so suddenly you get a rain. Okay, so rain in our area, and due to this rain here, the temperature is reduced. Okay, so before returning to the normal, the temperature is reduced. So if this rain has occurred in between the sampling times, for example here, so if I am taking the uh, recording the temperature at 12 o'clock in the afternoon and 3 o'clock in the afternoon. So in between 12 o'clock and 3 o'clock, so I got rain for about 20 minutes to 30 minutes. Okay. So due to this, what happens here? So that there will not be a major variations in the temperature. Okay, so there will not be major variations in the temperature. Why? Because the rain has occurred between our sampling times, that is between our recorded times. Okay, so due to this, whatever the things we are recording would not have the effect of the rain. Okay, so the our sampling time was too slow to catch the changes in the weather. Okay, so if you had increased the number of samples, that means if you have increased the number of samples furthermore, we would have recognized the changes in the weather. For example, instead of taking 8 here, so if we are taking 20, for example 24 samples, that is per hour one sample means, so we can able to record the variations in the temperature more neatly. Okay, so this thing what we have to make sure is that, so the so in order to get the accurate digital signal, so we have to increase the number of samples. As it turns out, the Nyquist criteria, the Nyquist criterion will define how fast the sampling rate needs to be represent an analog accurately. Okay, so the Nyquist criteria defines how fast the sampling rate need to be representing an analog signal accurately. So this criterion requires that the sampling rate is at least 2 times the highest frequency contained in the analog signal. So therefore, the sampling frequency is equal to 2 into F max. So where F max is the highest frequency contained in the analog signal. So in our example of recording weather, so we need to know how quickly the weather change, how quickly the weather can change, and then take sample twice fast as that value. Okay, so it is the sampling frequency here. So f sampling is the sampling frequency which is required to accurately represent the analog signal, and f max is the highest frequency of the sampled signal. And the next thing is, how much resolution should we keep to represent the analog signal? So how much resolution are the uh, quantization levels? How many quantization levels, or how much resolution we have to keep in order to represent the analog signal accurately? So for this, the answer is that there is no absolute criteria for this specification. So each application will have its own requirement. In our example, what we have taken is that, so here we are interested to take 25 quantization levels. So therefore, we have taken the 25 quantization levels. Okay, so if you want to take, you can take 50 quantization levels also. Okay, so in order to take the number of quantization levels, so there is no such criteria. You can take, depending on the application, how many quantization levels you want, you can take. But when you are going for the sampling rate, so we have to follow the Nyquist criterion. So this is about the uh, analog and analog versus discrete time signals, and how to convert analog signal into the digital signal. So this, the thing you have to keep in mind is that, so from this discussion, the main important thing that we have to keep in mind is that, so whenever we are converting the analog signal into the digital signal, so in order to make sure the same information represented by the digital signal and the analog signal should be same, when we take more number of uh, samples and more quantization levels. So if the quantization levels and the more samples are taken, so there will be no difference between the analog signal and the digital signal. Okay, so this is the first lecture in this a series of lectures regarding the digital circuits. In the next class, we will discuss about the importance of sample and hold circuit, and how these sample and hold circuits are used in the ADC. Okay, so that's all for the day. So thank you.